Hello, my name is Ryan, and today I'm going to show you how to prove that two functions are inverses. Alright, so inverse functions, just a quick little review, is one function that undoes the other. So this function makes 3x plus 2, and then this function is going to undo that. So, if we have f of x and f inverse of x, if we do this, we do a sort of composition. If we plug one into the other, we can see that kind of like a square root and a square, these undo each other. So these should undo each other, leaving us with x. So that is what a true inverse function should do. So our goal is basically to use this composition. So I'll show you how that works. So for these two functions, we don't know if they're inverses or not. So we want to plug one into the other. So let's start by taking g of x and plugging it into f of x, like this. So that's going to mean we're going to take this function here and plug it in to wherever we see the x in f of x. So f of x is going to look something like this, right? With the x is usually here, but when we're plugging in, we're going to plug in what g of x is equal to. So x minus 2 over 3. And we can already see this is starting to cancel. So we're dividing by 3 here, and then we're also multiplying by 3, so we can just cancel those out. Those are inverse operations, leaving us with x minus 2 plus 2. These cancel out as well, leaving us with just x. So that's one way. Now we also need to do it the other way. So we have to do g of f of x. So we're going to start with the g of x on the outside, which is this quantity minus 2 over 3. And then we're plugging in our f of x where we see the x in here. So 3x plus 2. So we can already see again that this 2 is going to cancel out, leaving us with 3x over 3. And these 3's cancel out, leaving us with just x. So these functions are indeed inverses. And you can also prove graphically by using the graphing calculator to show. I'll show that right here. And you can see that they're just a reflection over the line y equals x. Okay, now I'm going to show you a more difficult example. Okay, so this function is x minus 4 over 2x minus 5. It's a rational function, so that means that there's an x in the bottom as well. So what we're going to need to do here is we're going to first need to find the inverse function. So a lot of times it's going to ask you to find and then prove the inverse function. So I will find the inverse function. Just a quick little review. We're going to switch the y and the x. So this f of x is the y, and then the x is here. So we're going to just switch those. So x is equal to y plus 4 over 2y minus 5. And then we're going to begin to isolate that y. So the first thing we're going to do is we see division here. So to cancel that out, we're going to just multiply 2y minus 5. Then we're going to have to do the same thing to the other side. So we get x times 2y minus 5, which we're going to distribute that x. So 2xy minus 5x is equal to, and then these are going to cancel, leaving us with just y plus 4. Now, when we have a situation like this, what we're going to want to do is we're going to want to move all the terms with the y on one side that we want to isolate and move all the other terms to the other side. So we see a y on this side, we're going to move it over to this side by subtracting it. And then we see a 5x on this side, we're going to add to the other side. Now we've got 2xy minus y equals 5x plus 4. So all the y's on this side, all the other terms on this side. And what this allows us to do is it allows us to factor out the y, leaving us with 2x minus 1. And that's going to equal 5x plus 4. And then now our final step to isolate the y is divide by 2x minus 1, leaving us with the inverse function f inverse of x is equal to that 5x plus 4 over 2x minus 1. Alright, so now we're going to do the new part, which is in the composition. So let me erase this. A little more space, because this does take up a lot of space. So let's begin with f of f inverse of x. So let's start with the f of x, the outside function. So we're going to leave a space. Plus 4 over 2 times minus 5. And then we're going to plug in the f inverse, where we would usually have the x. 5x plus 4 over 2x minus 1. And then, same thing down here, 5x plus 4, 2x minus 1. All right. Now, the first thing I see we're going to do is we're going to distribute this 2, leaving us with 10x plus 8. I'm just going to write that down here so I don't forget it. And then I'm going to make common denominators. So all of these numbers are actually over a 1 as well. And in order to add fractions with different denominators, we have to multiply to get common denominators. So how we're going to do that is we're going to multiply this fraction by 2x minus 1 over 2x minus 1. And same down here, 2x minus 1 over 2x minus 1. And then when we distribute all of these terms, we're going to left with on the top 5x plus 4, that doesn't change. And then we're going to expand this to one fraction, which is over 2x minus 1, right? Because we're adding these fractions and using the common denominators. Then we're distributing that 4. 4 times 2x is 8x. 4 times negative 1 is negative 4. And then that is the entire numerator with the denominator 2x minus 1. Then in the denominator, we already distributed that 2, so we end up with 10x plus 8. This is all, again, over 2x minus 1. And then we're going to distribute this negative 5. So, negative 10x, and then negative 5 times negative 1 is positive 5. All right. So now we see a fraction where the numerator and the denominator are both over the same thing. So if we have that, we can actually just remove the denominators, the 2x minus 1. Because if we had 1/3 over 2/3, that's going to have the same value as 1/2. We don't need those denominators when we have a fraction, but only when we have a fraction. So we can actually just cancel those out, leaving us with 5x plus 4 plus 8x minus 4 over 10x plus 8 plus negative 10x plus 5. Now we can already see that some things are canceling. This 10x is canceling with this 10x, this 4 and this 4, leaving us with 5 plus 8x, 13x, and then 8 plus 5, 13. And this crosses out to give us x at the end, which is what f of f inverse of x should equal. All right, so we've proved one way. Now we need to prove the other way. So we are going to take the f inverse of f of x. So write out our f inverse, 5 times quantity plus 4. We know we're going to have to do the same process again of common denominators, so I'm going to already write that over a 1. And then 2 times the quantity minus 1 over 1. Same deal. All right. So let's plug in that f of x in there. X plus 4 over 2x minus 5. And then 5x, or x plus 4 over 2x minus 5. And then we can once again distribute. And then we'll also do the common denominator again, but this time it'll be 2x minus 5. All right, then I'll write that big fraction again. So 5 times x, 5x, plus 4 times 5 is 20. And then we're going to go over to here. 4 times 2x is 8x. Remember, this is all one big fraction because I made a common denominator and I'm adding my fractions. And 4 times negative 5 is negative 20. All over 2x minus 5. Then again, 2 times x 2x. 2 times 4, 8. And then the negative 1 distributed here, negative 1 times 2x, negative 2x. Negative 1 times negative 5 is positive 5. This again over 2x minus 5. And then same deal as last time. When we have both the same denominator, we can cancel it out. So, and then we're going to actually simplify a bit sooner. So we see 20s are going to cancel. 2x's are going to cancel. So we have, again, 13x over 13, which is equal to x. So these functions have been proven to be inverses. All right, now I'll have you a couple for you to do on your own. Okay, this first one, I'm going to want you to find the inverse function and then use composition to prove that they are the inverses. I'll give you a moment to pause and do it on your own. All right, now I will do it. All right, so we're going to switch our x and our y. So x is equal to square root of 3y plus 2. Then we're going to use the inverse operation, squaring both sides. So we have x squared equals 3y plus 2. Now we can use subtraction here, x squared minus 2, and then we're dividing by 3. That is the inverse function. All right. Now to prove these two functions, we're going to use composition. So f of f inverse of x is equal to, so the f of x is the square root of the quantity 3 times the quantity plus 2. Quantity is x squared minus 2 over 3. Now we can already see that 3 and that 3 are going to cancel, leaving us with x squared minus 2 plus 2, all in the square root. These 2's cancel, leaving us with square root of x squared, which is just x. Now for f inverse of f of x, we will plug in, we'll start with our f inverse, which is the quantity squared minus 2 over 3. And that quantity is square root 3x plus 2. First thing we can see, the 2 and the square root are going to cancel. Or the squared and the square root are going to cancel, leaving us with 3x plus 2 minus 2 over 3. That plus 2 and minus 2 cancel. We're left with 3x over 3, which is x. So these are both proven to be inverses. Show you a couple more. All right, our next problem is going to be f of x equals 9x squared plus 30x. So we're going to start by finding the inverse, again, switching x and y. So x is equal to 9y squared plus 30y. And then here we can see what looks like the beginning of a perfect square trinomial. And if we look at our perfect square trinomial formula, it's a squared plus 2ab plus b squared, and that is equal to a plus b squared. So if we look, our a, this first term, squared is going to be 3y squared. When we distribute that square, we get 9 times y squared. And then this, in the middle, if we divide by 2, we get 15y. So that means 15y is equal to a times b. If we divide 15y by 3, y, which is a, we get 5 for b. And then this is going to be b squared, so we must add 25. But we also need to add 25 to the other side, because it's an equation and we want to keep it equal. So just erase this real quick and continue. Okay, so now we can express this as a plus b squared. So 3y plus 5 squared, that's equal to x plus 25. Then let's take the square root, leaving us with 3y plus 5 equals the square root x plus 25. All right, now subtracting 5 and dividing by 3, we get square root of x plus 25 minus 5 over 3. And that is equal to f inverse of this function. All right, now I'm going to have to erase some in order to prove this because this is going to take a little bit longer. Just a quick note about these two functions. They're not true inverse functions because this function here is a parabola and it does not pass the horizontal line test because it's a parabola like this. So its inverse would look something like this, which would not be a function because it has two outputs for some one input. So we would need to restrict the domain. And we could restrict the domain by using the vertex formula, opposite of b over 2a, in the quadratic ax squared plus bx plus c. So the b would be 30, so opposite of b would be negative 30, over 2 times a, which would be 18. So this would be the x-coordinate of the vertex. So we could say that when x is between negative 30 over 18 and infinity, the inverse function is this function here. Just a quick little side note. All right, perfect. Now we have enough space. We're going to first take f of f inverse of x. So we start with our f of x. We get 9 times the quantity squared plus 30 times the quantity. So we're going to put in square root of x plus 25 minus 5 over 3. And then the 30, we're also going to do the same thing. Okay, so now we're going to have to square this whole thing. And the square distributes to every term. So this is a term, and then this is a term, because we only have subtraction in the middle. So we need to have one term. So x plus 25 in the square root, so this minus 5, this squared is going to be, so the first term squared is x plus 25. Then 2 times the product of these terms, which is our formula for squaring a binomial, is negative 10 times square root of x plus 25. And then finally, square the last term, we get plus 25. So that is this squared. And then that's going to be over 3 squared, which is 9. And this is all going to be times 9 as well. So these 9s will cancel, leaving us with this plus, then we have 30 times these. The 30 and the 3 can reduce to a 10 there. So then we have 10 root x plus 25 minus 50. So we can see the minus 50 cancels the two 25s because 25 plus 25 is 50. Then we have x minus 10 times the square root of x plus 25. Then positive 10 times the square root of x plus 25. These will cancel, leaving us with simply x. That is the first case. Then the second one is going to be f inverse times, or f inverse of f of x. And that is going to be equal to, if we start with f inverse, we get square root of quantity plus 25 minus 5 over 3. So the quantity is 9x squared plus 30x. And then we know this is the perfect square trinomial that we formed earlier. So this is 3x plus 5 squared under the square root minus 5 over 3. So this square root and the square cancel, leaving us with 3x plus 5 minus 5 over 3. The 5 and the 5 cancel, leaving us with 3x over 3. The 3's cancel, leaving us with simply x. And that's my last example. You can also prove all these functions by graphing and composition. Those are the two ways to prove these inverse functions. Thank you for watching. If you have any questions, please leave them in the comments, and have a good day.